Okay, so good morning, GeeCON. My name is Ionut Balosin. I'm software architect. I'm currently working for Luxoft, and apart the software architecture activities, I also conduct technical trainings, especially on Java performance and tuning and software architecture topics. If you'd like to know more details about me, you can get directly in touch with my Twitter or directly on my website. These are the words about me, and let's see what means to demystify, because I see quite on fashion this word at the conferences, and also for GeeCON there are other two topics containing the demystify. As per Cambridge Dictionary, it means to make something easier to be understood. However, my definition is this one: to make Java language features easier to be understood by revealing the internals, how they work internally behind the API actually. So this is the main of my talk. And I was quite inspired by Richard Feynman. He has a famous quote said that explore the world, everything is nearly interesting if you go into it deeply enough. So that's my rationale, and this is how I structure the talk. The agenda for today contains few things actually, and of course it's subject to me what are the most important features from JDK 9. However, today we will discuss about all of these topics. Few words about my configuration, because also I did few benchmark tests in order to prove some timings in terms of response time or throughput. All the tests were conducted on Ubuntu using JDK 9, of course. I used Java Micro Benchmark Harness and Eclipse Memory Analyzer in just one case. And of course, few things about the hardware, the CPU, and the memory. All of this being said, let's zoom in inside the first topic, which is basically private interface methods. What says the private interface method? The feature itself is part of JEP 213, which delivers actually more small features. Apart those features, also the private interface methods. And let's see in practice how it works and how we can use it. Suppose you have a private method, as you can see, the print method, which is referred by the foo method, which is a default method declared inside the interface. So this is the context. For example, you can use these private methods in order to segregate, to better structurize the default methods added in JDK 8 for the interfaces. However, let's see how it works internally under the hood. So for example, if you compile this interface and decompile it, at the bytecode level, there is the invoke special opcode. The invoke special opcode, it's a bytecode opcode that is used also to call, for example, private class methods. So there is nothing specific, no explicit behavior in terms of handling this private interface method. It's the same principles as you, for example, have a method inside the class and you call a private method out of it. On top of that, as you can see here, the default, it's not the keyword at the bytecode level, which concludes that the default keyword is just a keyword that exists at the Java code level. Where if you compile and you zoom inside the bytecode, there is no default keyword. So this is about the private interface methods. There is no specific behavior. They are handled just the normal private class methods. The next category is in regards to static interface methods. The same example, you have a static void bar method, which dispatches the call to the static print, which is a private static interface, which does a system.out. If we compile and decompile and zoom in inside the bytecode, we will see that invoke static call. Invoke static is the same way of calling any other static method. Again, there is no specific behavior or no opcode added for these private interface methods. These are the principles, but now let's study a more interesting example. By interesting here, I'm referring to the following scenario. Let's have an anonymous class casted to a functional interface using a private method reference. How does this look like? We have the iFunctional interface, which has the method run in it, very simple, and we have the method, the class, main, which contains the public interface inner, you can see at the bottom, and this private interface inner has the private print inner. So basically it contains a private interface method. However, in the main method, what we have actually, we instantiate the inner, we explicitly do the cast, we use the resolution operator to refer the print method, which is actually the private interface method, and then we call, on that instance, we call the method run. However, this concludes what I was talking about. However, let's try to understand how it works under the hood, because as you might see, it generates a lot of additional classes and syntactic methods. So let's figure out on these two lines of code, the assignment and the call to the run method. First of all, what we have basically a new inner, and we create an instance of that anonymous class. Under the hood, javac generates a main $1 class, which is a class generated on the spot by javac when you compile such code, because you instantiate that anonymous inner class, and the bytecode you have it on the left, it's new dap invoke special. This is the pattern every time you create, for example, a new instance for a new class. This is the pattern, new dap invoke special. However, if we search and look inside the main $1, which was automatically generated by javac, I was saying, it implements, of course, the inner interface, and javac automatically adds the default constructor. So it's very simple. However, for the print, when you are using these private reference methods, these are desugared actually using an invoke dynamic. I won't detail too much about invoke dynamic, because there are a lot of talks on this topic and there is a lot of information. However, keep in mind that in our case, the private interface method being referenced, it was desugared using an invoke dynamic. And if we zoom inside that invoke dynamic, we might surprisingly see that there is a the lambda main $0, which, why I was saying it's surprisingly, because it belongs to the main class. However, we didn't declare any method in that class, right? We just had the main and our interface inner. And this is so-called syntactic method. Those kind of methods are automatically generated by the javac, and I'll get back on it and I will explain you by a sequence diagram how it's working. However, this is the implementation. So if you zoom in, you will see that it just does a dispatch call towards another method. So this is our syntactic method generated by the javac. Nothing else, it just dispatches the call. And the invoke dynamic, once it is hit during the runtime, so once the call site is hit, roughly it returns an instance of that functional interface. However, what is my functional interface? Is that iFunctional interface that contains a declaration of the method run. And how it is desugared, actually how it looks like, that kind of instance, it's basically an instance of a VM anonymous class, which is this main $lambda 49. And let's see how this look like and when it is generated. In theory, and in practice as well, these VM auto-generated classes are generated, for example, when you are using lambdas. And you can see all of them dumped to a specific path if you are using, for example, the JDK internal lambda dump proxy classes. So by default, it's disabled, but if you specify this flag once you start the JVM, you will find out all of those classes. However, if you start a JVM with verbose class, you will see in the printings a lot of such VM anonymous class automatically generated on the spot. The 49, what says 49, and this is the naming convention, it starts with the enclosing scope, because the main it's the enclosing scope is the outer class. It has $, lambda, and $49. What's that 49? It's actually a counter, an atomic counter, which belongs to the factory, because every time when a new VM anonymous class is generated, the counter is incremented. So in this case, 49 stands that this is the 49th class generated when the JVM started. Apart this, what you can see a constructor, you can see a get lambda, which is, by the way, referred by another method handle, and at the bottom you can see our method run. Why is the method run? Because recall the lambda 49 should implement the functional interface, and the functional interface has declared the method run in it. And as you can see here, it's quite simple. It just does a dispatch call towards our synthetic method that we discussed previously. So let's see how the chain of calls are triggered during the runtime. Suppose the call.test is run. The bytecode is quite simple. It doesn't invoke interface. Why invoke interface? Because actually the run belongs to an interface. And first, when it says test.run, what happens? Actually, the method run, which is declared in main, invokes the main $lambda 49, and this method, as we saw, it's a quite very trivial method. It just does a dispatch back to the main, to the synthetic method generated by the javac inside the main, as we saw, which on its turn, it even dispatch furthers all the call to the main $enal $access 00. You might wonder, what is about this $000? Recall, we used a private method. So every time you refer private methods for other classes, javac automatically adds these access methods in order for us to be accessible from the outer scope, because for the JVM there is no notion about the inner class. So this is the trick. So it dispatches the call to the main, which implements the inner, main $1, which implements the inner, and in that access method, the implementation, it's pretty simple. It forwards the call to the print method. So in the end, the print method does the system.out. So as you can see, there are a lot of chaining in terms of calls in directions, classes generated, synthetic methods, and so on, just to dispatch this and to handle the run call at the runtime when the call site is hit. But what about the next scenario? In the next scenario, I kept the same example. It's the same. However, I decide to remove the inner. You can see the explicit cast. Let's suppose we remove the explicit cast. And the question for you is, what do you think? It will compile or not? And there are only two questions, yes or no. Who's for yes? Okay, and for no? And the others? Okay, the thing is that if you remove the explicit cast, it doesn't compile. And it might seem a bit puzzled, because we know actually that why it shouldn't compile. However, in the first case, the print method exists. It exists, of course, but remember, new inner during it's basically an anonymous class, and this anonymous class doesn't have direct reference to the print method. Why? Because the print method, it's a private method, and the compiler, it's right in rejecting this. However, the diagnosis is wrong. It shouldn't. We shouldn't, for example, get that compile time exception. And in regards to that, there is a JDK task to hopefully it will be fixed and delivered with JDK 11. So this is the limitation. The next thing is about strings in JDK 9. I won't go into a lot of details. Also, yesterday Monica offered a bit of background how the strings were improved and the rationale behind that. However, few things. The string, recall until JDK 9, there was a char array. All the strings were backed by a char array. However, because in practice there is huge footprint, memory footprint occupied by a lot of strings that could, characters that could fit 1 byte, for example, Latin 1. That makes sense to compress them and to use the Latin 1 encoding scheme. However, if the characters couldn't fit Latin 1, and for example, there are 2 bytes for 1 character, it switches back and uses the UTF-16 scheme. And this feature, it's called compact strings, and it's enabled by default in JDK 9. Here it's the graphical representation. Let's suppose we have a string. We create an instance of that string which contains javac. Very simple. Using the UTF-16 encoding scheme, how it looks like, for each letter, as you can see, there are 2 bytes. All the times, one of those bytes, it's useless because it's 0. We don't need it anymore. However, in Latin 1, in the compressed version of it, we somehow minimize the footprint, removing that irrelevant bytes, which are 0 all the times. If we also measure how it looks like, and here I use, for example, Eclipse Memory Analyzer for these 2 print screens. UTF-16, the same string, the retained heap has 56 bytes. In regards with Latin 1 alternative, which has 48. You might say, of course, 8 bytes, it doesn't matter. It matters because in reality there are a huge number of strings. If you profile your application and you will see the histogram, there are a lot of strings. And of course, the footprint is dramatically reduced. However, if you have strings where there is just 1 character which couldn't be compressed, which is the case for this javac, you see, notice the last C has the accent. Even in this case, Latin 1 scheme couldn't be used, and it is encoding using UTF-16. And this is the basic theory around the strings and why they were compressed. However, it comes at a cost. What's the cost? Because recall, UTF-16 strings now are backed by a byte array, and 1 character corresponds for 2 bytes in that array. And this brings to a limitation. This is a code for the JDK sources, because in case of UTF-16 strings, you can half the size. You can create characters using the maximum integer, because by default you can allocate an array, it's the maximum integer size, the length of it. However, using this encoding scheme, because 1 character is backed by 2, it halves actually the size, and if you try to do that, that's no problem, but you will get that error. UTF-6 times it's that one, and should be less than integer max value divided by 2 actually. So this is the penalty we pay for things that doesn't happen in case of Latin 1 strings, or previously where all the strings were backed by char array, because you can allocate up to integer max value, the array length. This is another thing regarding string construction. Now, if you are using JDK 9 and with the default compact string, implicitly it goes and tries to compress the strings implicitly, because the compact string feature is enabled. It tries to compress that string. However, if it fails, it switches and uses the UTF-16, the normal encoding scheme. And you might see that in case of your applications have a lot of UTF-16 strings, what is the performance? Because it tries, it fails, and switches back to UTF-16, right? This is how it behaves, relying on the default. And here what I did using the GMH, I took several strings, like 5 strings actually, all of them backed by UTF-16 encoding scheme, and I tried to measure 2 ways actually the time spent using the compact string. The first line, it's the default feature, and without compact strings. And as you can see, actually without compact string, it spent around 35.7 nanoseconds per operation. Its response time lower, it's better, which concludes that if you have applications in practice also, if you have applications that relies the majority of your strings are UTF-16 strings, why not relying on this mechanism and try to disable actually the compact strings, which comes default, and measure the performance. It's free, so it's just a mechanism of leveraging and decide if it works on your application. Another challenges with this is when you compress, for example, because you have a byte, and it is compressed, and you want to get the char representation out of it, or the char array representation out of it. Why? Because the string API contains few methods, for example, char at or toChar array, which returns actually the char. However, under the hood, the string is backed by a byte, right? Because this is how it is handled. And you can see the snapshots for each method from the JDK sources. What it does, the Latin one, it's quite simple. In case of UTF-16, it basically merges both bytes and returns the char representation. And this is called the inflation, when you have a byte and you return a char out of it, the inflation scheme. And I did some tests because I was curious in JDK 9 how the performance is impacted. And I took these 2 methods, toChar array and char at, and I created a few benchmarks using Latin 1 and UTF-16 strings. As you can see, for example, the first string it's Latin 1 and the second it's UTF-16. Why? Because it ends in those weird characters which couldn't be compressed. So implicitly it is stored using UTF-16. So I test this using also JDK 8, the last update that I found available. And as you can see, for JDK 9, if we look only at the char at for Latin 1 and UTF-16, there are 3.3 versus 3.0 nanoseconds. I wouldn't say it's too much of difference. However, in JDK 8, it was very, very slight better. However, I would like to quote Cliff. He said that fast enough, it's fast enough. So as you can see, the performance wasn't impacted. It's quite very, very marginal. The same for toChar array, Latin 1 UTF-16. JDK 9, for example, it took 11.9, and UTF-16 toChar array took 12.5. So I conclude that it's not a big discrepancy in performance. However, in JDK 8, at least in my measurements on my hardware, because I did all the measurements on my laptop, it took 11.7 nanoseconds. So again, not quite a big discrepancy in performance, so it's almost there. The next interesting case is the equals, because we see the strings are backed by this encoding scheme, and there is the coder which basically says that it's UTF-16 or Latin 1. And it's very important to understand that if you have strings that are backed by different encoding schemes, when you use the equals method, if the coders are different, it just returns false, right? Because it doesn't make sense to compare the actual bytes, because the coders are different, implicitly the strings are different. And conclude me to the following test. I took two strings, I mean two groups of identical strings, and I tested the equals method for between Latin1 and Latin1 identical, UTF-16, UTF-16 identical, and different strings like Latin1 and UTF-16. So these are all the cases we might cover. And as you can see here, using compact strings, the JDK9 default option, the last line, Latin1, UTF-16 equals, it took 2.8 nanoseconds, which is very fast in comparison to the others. And why it's very fast? Because it doesn't actually compare the bytes, because the coders are different, the strings are backed by different encoding schemes, so they are different. So let's return false from the start. However, in case of Latin1 with compact string, it was slightly better. Why? Because probably Latin1 are backed by few bytes in that array in comparison UTF-16. UTF-16 byte array, it's doubled. In case of using JDK starting without compact strings, the last column, the timings are almost there. So this is a very important thing to keep in mind, to take away, that if the strings are backed by different encoding schemes, the comparison it's extremely cheap actually. The next case, it's about how this code is it's desugared at the bytecode level. Prior JDK9, if you concatenate several strings, how it was tackled? Using string builder, right? In JDK9, if you concatenate many strings, they added the invoke dynamic with different strategies that are managed during the runtime. What's the meaning of that? Because until JDK9, the optimization was coupled to the to the bytecode. So if you concatenate strings, they are desugared until JDK9 with string builder, append, all this kind. It is very coupled to the javac, and it's also more difficult, for example, to break the compatibility at the bytecode level, because you have to recompile again and again. However, doing it in a very loose coupled manner in the runtime using this string concat factory and relying on the invoke dynamic, you can just upgrade your JDK version and you benefit of such features. So this is the idea of what I've explained. So there is a loose coupling between the way the string is managed during the runtime by keeping the same bytecode. However, there is a tricky scenario. If you, for example, test string concatenation in JDK 8 and JDK 9, let's suppose we have string concat, the class, which contains a method main, and that method main, what it does, it creates an instance of a message and tries to says system.out message, which what it does, it calls method toString, which is defined inside the inner message class, which has defined also an array of strings. For example, Java conference is the array of strings, and every time you call the toString method, it basically increments the index and prints the next string out of that array. Surprisingly, if you compile this and run it with JDK9, what it prints Java conference, as we might expect, because it prints message 0, message 1. So the 0 is Java, and message 1 relates to conference. If we compile and run it again with JDK9, it prints conference Java. So the order is different, as you might notice. What happens actually, and how to fix this, a quick fix is to run it again the same by specifying the explicit string concat strategy. In my case, it was bc_sb sized exact. There are few such bytecode generated strategies. BC, all of them starts with bc_something, so you can choose whatever strategy you want. However, all the strategies that relies on method handles, implicitly the default one, it's mh inline size exact, have some issues. And that's why there is another task raised. It's fixed at this stage. To not print, I mean, all of those method handles strategies were flown, and they print it in reverse order. So be careful with this situation if you are facing this scenario in your business applications. You just switch the string concat strategy and it's fine. Or upgrade to JDK 11. The StackWalker API. The next nice feature was in regards with the StackWalker. What it does actually, it works to the stack frames, and it prints, it inspects all of those stack frames in a lazy way. You can also limit the number of frames, and you can also filter the same. Recall until JDK 8 there was that thread get current stack trace, which implicitly filled with all the stack traces, and you pay the cost to create that stack element, stack trace element array, which even if you are interested in, for example, to inspect few of them, you pay the cost for all. However, this walking API, stack walking API, it's a nice way of doing that in a lazy way and to limit the depth. How it looks like, it's quite simple. It's based on get instance. You can also use few options. For example, across those options, the first one is in regards to it including, for example, the color class, if you want to include also the reflection frames, or the last one, show hidden frames. For example, if you have lambdas or frames belonging to those synthetic methods that we discussed previously, you should implicitly add that one, because by default in the stack trace they are not included. And also the last line is with estimate depth, which, for example, if you are interested in only inspecting the previous 10 or 20 frames, you can do that. And I did a test. What I tried actually, I had a method which recursively called itself until a certain stage, and once it hit that certain stage, I just wanted to measure the cost of inspecting the current stack frame, and the representation is in this diagram. The code, how it looks like, it's also not complicated. The benchmark method calls a recursive method that it's called again until it reaches a depth. Actually, I decrement the depth until it lowers down to zero. And in that case, what I take only the first frame. So using the StackWalker API, StackWalker get instance and give me the first frame. In comparison with the classical approach, in the classical approach, what we can do is, for example, we say thread get stack trace, and as we were saying, all the stack trace elements are filling, even if you take only one, so it's very, very inefficient. And these figures prove that in case of StackWalker, using different stack depths, for example, 1, 10, 100, 1000, all the times the number of microseconds per operations was lower in comparison to the stack trace. And another noticeable remark is that get stack trace is proportional to the depth. So for example, if we test even more and for example create 10,000 for the stack depth, probably the StackWalker will be slightly slower, but get stack trace definitely will be around 1 order of magnitude lower. So this is the idea, and this is the advantage of using the StackWalker API. However, there is a corner case, and this is basically something that you should keep in mind. If you have applications where you afford, for example, to throw these frames and to process them later on, instead of using the classical approach versus using StackWalker API, it's much even faster. What it means actually. Suppose you are on the thread 1, you create this throwable, and just it only creates the throwable, and dispatch the instance to another thread and try to process the frames in an asynchronous manner using the classical API, versus the synchronous version with the StackWalker, because with StackWalker you need to process it synchronously. So the caller thread, on the caller thread all the times, because otherwise you might get inconsistencies. So this is the idea, throwing something and processing it asynchronously versus processing it synchronously using StackWalker API. And as you can see, the StackWalker API, the first line, was slower in all the cases. However, the new trouble, because I measured only the new trouble, so basically the cost of creating a trouble and dispatching it to another thread. Of course, I didn't include the cost of inspecting the trouble instance, because suppose if you have such context of high performance application and if you afford to just create, throw in it and process it asynchronously, it's much faster than even using the StackWalker API. And probably this is another tip that you can take away out of this talk. And if it is affordable, why not refactor and use it in your code? Collection factory methods. In JDK 9, starting with in the JEP 269, so-called factory methods. So roughly, it's a very compact and nice way to create unmodifiable collection instances. And as we can see here, there is list of, set of, map of entry. So it's very nice and compact. But let's see how it was implemented under the hood, because the presentation is called Demystifying, right? If we zoom inside the JDK, you will see a lot of redundant methods, redundant by the name itself, but in terms of parameters, as you can see, there are different number of parameters until 10 fixed parameters. Starting with the 11th parameter, there is a varargs, the last line. So if you call the off method with less than 11, one of those fixed methods, it's implicitly called. However, if there are 11, 12, and so on, the varargs version is called. And the question is, of course, why? Would you write such code or no? Yes, why? Yes. Performance, of course. So that's the answer actually. How it works? Here it's a bit of assembly. I know we are Java and we love actually assembly, and that's why I added it here. Just to prove actually what happens when you call a method backed by varargs. When you call such method, there is an overhead of allocating a new array, of getting the fields from the stack, moving those, the parameters, moving those parameters inside the array, and then the last one calling the varargs method, which comes at the cost, of course, because you pay the cost of extra stack parameter manipulation and that array allocation. Also, I did a quick test between two versions of a method, one with explicit number of parameters and one with varargs parameters. And in all the cases, the one with the explicit method of parameters proved to be quicker, because in that case, there is no penalty of extra parameter manipulation and array allocation. So that's why the Oracle guys decided to create those fixed methods until a certain number of parameters and then switch to the varargs. On top of that, if we zoom inside the off methods, they are backed by these wrappers, list 0, list 1, list 2, n. List 0, 1, and 2 are custom wrappers in case of 0, 1, or 2 elements. And the last one, list n, it's basically a wrapper that comes in place if there are more than 2 parameters. Started with the third one, actually. How those looks like? List 0, it's the top one. It's basically very simple. It contains nothing. List 1 contains only one element. List 2 contains E0 and in1, 2 elements, and then is the array that I was talking about. And you might think, yes, but still, why it's such mechanism? So the mechanism is pretty simple to be understood. If you know a bit of how a CPU and what's the memory layout of such structures, you will understand. In all the cases when you have an array, there is an implicit indirection during the runtime to get the elements array from the virtual memory. However, there are chances that using the array, the elements themselves to not be collocated, and for example, calling the first element from the array because there is an indirection for the second one to not be on the same CPU cache line. So you might pay the cost of a CPU miss. However, if they are compacted or packed, if you get the first one, E0, as it was the case for the list 2, if you take E0 and E0 and In1 could fit in the same cache line, both of them are, by just calling E0, you have implicitly E1 on the same CPU cache line. So still, again, the performance is the answer. Oh, this is another interesting remark you should take into account. However, if you, in JDK 8, what was the alternative to create such an unmodifiable list? It was you allocate an array, and what you said that you are using collections.unmodifiable list versus JDK 9, which the API was quite short, list.off. In terms of footprint, how many classes are created, what's the cost of them, this is the representation for JDK 9. In JDK 9, you see the unmodifiable list, and there are few pointers of indirection. To the first one is towards unmodified random access list. It refers the array list. It refers the object array, which has references to the elements themselves. So in practice, if you measure and create such instance, you measure it, it has around 104 bytes for the retained heap. As in comparison to the JDK 9 option, JDK 9, as we saw, because it's list to the wrapper, contains E0 and In1 packed. Of course, the number, the footprint, it's minimized, it's reduced. So the retained heap measured by Eclipse Memory Analyzer in this case was 24 bytes. So it's much cheaper, more compact. Here I measured, for example, the performance between off method and unmodifiable list, the creation time actually, using different number of elements, 1, 2, 3, 10, 11. And in all cases, the off method proved to be faster, quicker, which leads me to the final conclusion that these factory methods have better reference locality, it preserved the space, and also based on the previous test, the creation, it's faster. In case of set, it's the same. I will go quickly to the methods. I won't get into the same explanation. There are dedicated methods for fixed number of arguments, and starting with the 11th varargs, there is the varargs method. And the same for the wrappers, set 0, set 1, set 2, and set n, the same principle. And in terms of performance, again, I did few benchmark tests, and the off method, the off version, was always better in comparison to the alternative that we were using. For example, we might use in JDK 8 unmodifiable set. The map of same methods of methods for less than 11 key value pairs, and starting with if you want to, for example, create an unmodifiable map with 11 such pairs, you can rely on off matrix, which is a vararg implementation. The same wrappers, map 0, map 1, and map n. And performance is, in case of off versus unmodifiable map, I mean the JDK 9 versus JDK 8 version. In such case, I would see that in few cases, in few scenarios, for example, for 2 number of elements, the off method took 39 versus 40. In case of 3, 4 and 10 as well, the performance is not very different. However, of course, the footprint in case of using unmodifiable map, it's much bigger because you saw the number of references in case of lists. So it's the same in case of maps, actually. And in all the cases, the off entries version, the last column, the red ones, they were slower because, of course, you know now that you pay the cost for the var args, overhead, and so on. The next one is onSpinWait. This is quite interesting because it was added in JDK 9 and it belongs to the thread class. What it says basically onSpinWait, in the context where you busy spin inside a loop, waiting for some external events to happen, this fits very good in such scenario. Because, for example, I will get back into the internal details, how it works internally, but it is very useful when you, for example, the rate of events is very high and each event happens quickly and and finishes very quickly as well. So you don't want to release the CPU slice. You still need to be scheduled by the OS, because you are waiting for such huge number of events waiting to happen. And this is the sort of pattern. So while you are waiting for a condition which is not satisfied, however, the condition should happen very frequently and should finish very quickly, you can say thread onSpinWait. Pattern, more approachable pattern in real life is the producer-consumer. For example, inside the producer you have a lot of elements. You try to produce. Since you are not ready to produce, you say thread onSpinWait. And then if the event happens, ready to produce, invalidates, and you produce the item and continue with the next one. The same for consumer. While the consumer it's running until it receives the signal finish from the producer, it asks itself, am I ready to consume? Yes or no. If I'm not ready to consume, spin wait and then consume. How it works at the hardware level, it's backed by pause instruction. The pause instruction, it's a x86 instruction. By the way, it's not a new instruction. To my knowledge, it's since Pentium 4. However, this onSpinWait was recently added and it's backed by that instruction. It's intensified by pause instruction. What pause instruction does, it's a hint actually for the CPU that I'm in a busy waiting loop. So in this case, I should delay a bit the execution. I should emit less instructions. So implicitly in the pipeline, there are less instructions to be emitted because the execution it's a bit delay, and as a consequence it reduces the power consumption as well. However, how much it delays, as per Intel documentation, it depends from CPU to CPU. But this is what it does in reality. It basically delays but doesn't releases the slice. And I did a simple test. I looped for 1024 iteration, and inside the iteration I used onSpinWait, yield, and sleep 1, because you can also use sleep in your test, right? If you are waiting for very few slices. However, the very important remark is the number of context switches. The number of context switches in case of sleep, it's dramatically higher, because if you rely on the sleep, what does the OS schedules the thread. So you go into a context switch. However, in case of yield, there is just a hint for the OS that I might be able to be descheduled. However, I didn't finish my work, right? And you are actually at the OS scheduler mercy to be descheduled or not, depending on if there are threads, contention, priorities, and so on. In case of onSpinWait, you are not descheduled, but you just delay the execution. So that's why the number of context switches, it's lower for onSpinWait, and also the performance in case of onSpinWait, it's better because you pay less overhead. You are not descheduled. Still, there are context switches, of course, at the OS level, but not so many. However, if you are relying on this onSpinWait API, be careful, because on Spark architectures, it might not behave well. At this stage, as I found, there is a task for the JDK guys to investigate what would be the appropriate intrinsic for the Spark architecture. But on x86 platform, it works well. The last part of the talk is contented logs, so I go quickly to it. It's quite short. The contention on the logs was improved. What means contention? Contention happens where, for example, you have a shared resources and multiple threads tries to access that resource. And in such case, the JDK 9 comes with this JEP, which improves the contented logs in few areas. For example, monitor, enter, exit, notify, notify all, unpark, and so on. How it looks like, the graphical representation, it's like this. Suppose you have a monitor and many threads tries to acquire the monitor. However, only one can do at a time. The others are moved to inside a queue, and they are waiting inside the queue until the thread that owned that lock releases it. It notifies the next one, and so on. And this monitor and the wait set are stored at the object level. So every object in Java has such by default. And I tested it with a very simple approach. I've created a synchronized method compute, and inside it I added a loop. I looped for 50 iterations, and I simulated a bit of heavy processing. What means heavy processing? Basically, I was using a volatile, which is very, very non-performant. So that's why I was saying that it's a bit heavy. And at the end, I measured the time by sharing the same compute instance, actually, across all the threads. And what I did, I just slightly changed the number of threads as it is in here. So I tested with 1, 2, 4, 11 until 1024 threads. On the right column, using bias locking and minus heavy monitor, this is the default JDK option. The default JDK option comes with bias locking scheme activated but without having monitors. And it proved that when the contention was lower on that method, it behaved better. However, if the contention increased, I mean starting with the 64 number of threads, 828 and so on, enabling explicitly and relying on this heavyweight scheme, which you can explicitly enable by use heavy monitors and disabling the biased locking, it proved to be faster. And this is another probably notice for you. If in your application have such shared resources or logs and you have a really huge contention on them, why not try to enable this explicit heavy monitor, the scheme itself, and measure again the performance. It might be better in some cases. So this is actually all that I had for you today. I'd like to thank you for quite an impressive audience. And here are a few references. If you are interested in more, you can Google and listen to the talks. They are published basically on the links on YouTube. So thank you all. If you have questions, but I think we are a bit late. If you have questions, otherwise you can catch me. I'm here until tomorrow evening, and I might be glad to talk to you. Thanks.